Okay. So welcome everybody again. Okay, looks like today there's finally some space for everybody to sit, right?
Yes.
I've heard from a few people that the video on YouTube is missing audio, and that's the case. Please rest assured that the video from the camera isn't missing the audio, and I have the proper files on my hard disk. So at some point when the good engineers of YouTube fix their transcoder, you will be able to hear the audio, and I'll try finding some other way to upload it and fix it as well. So I just can't promise you anything yet. It will happen at some point, but I don't know how long it will take until I find a format that YouTube can actually ingest and keep the audio. Okay. So there were a few questions about, signing up for projects and so on, and because you're not quite sure yet whether you're still on the wait list and all that. I think so if you're on the wait list and you got on the wait list after the deadline, it's probably okay. That afterwards then you say, well, okay, now I only signed up for a project team. However, I want to make sure that as soon as possible we actually do get project teams. The reason is, first of all, if you don't have a team, it's much harder to discuss with somebody what you're actually going to do. Secondly, if you have a team and later on you want to rearrange, well, we can still do that, but only under the proviso that in the end you always will have a valid team. So I want to make sure that everybody has a valid team at any given time. You can change the team if everybody in all the teams that you want to rearrange is also in agreement with that, but otherwise you can't. Third question, team sizes. Some people ask me whether they can please have a team of only 2 people. I think that's not a good idea, and it's not a good idea for 2 reasons. First of all, you can actually do more with more people. And I think with 3, you can actually do more than with 2 people. There's an optimal number, but I think that optimal number may not be 2. Secondly, at some point we will have midterm project presentations, and at some point final project presentations. Now, I only have limited amounts of time that we can allocate for those presentations, right? So if we allocate maybe 10 minutes for the midterm project presentation and 20 minutes for the entire presentation for the final, and you have teams of size 2, and you can roughly extrapolate how many days it will take us to go through all the presentations. In other words, it's not feasible. This is why I also need to essentially upper bound the maximum number of teams that we will have. So it's a very simple numerical exercise. Right? So this is why I'm reasonably insistent on keeping the number of people in a team bounded from below, and that lower bound is 3. If you have at some point trouble that nobody else will want to work with you, well, okay, I can help you. Okay, good. But then you really have to come to me and tell me, by the way, I've tried everything, and that includes posting on Piazza. Okay. Furthermore, if you have questions, if you can, please post them on Piazza. That way I might not only answer your question, but maybe somebody else as well. Okay, cool. Any questions from you guys before we get started? I mean, some of you already were at the office hours in the afternoon, and I hope you all got something out of it when you came. Good. Now, let's go back to exponential families and do a little bit more detail. There were some questions why I'm not putting all the slides on, or basically such nice book chapters online for each of my classes. I wish I had them. This is something I'm working on right now, but yeah, I wish I had all those chapters written. So once they are written, maybe some later generation of students will get them beforehand. Okay, we've done exponential families, and yeah, we basically looked at the Gaussian last time to see that the Gaussian actually has this nice exponential families distribution. And we basically made a dog's breakfast out of the expansion in the Gaussian, and so now we can safely assume it's a member of the exponential family. There's an interesting one, namely the Poisson distribution, And for that one, I'm going to go through the algebra just briefly to show you that the uniform measure is not necessarily the only measure that you may have in using an exponential families distribution. Okay. So what I'm claiming is that the sufficient statistic phi of x equals x, and the measure, counting measure 1 over x factorial will do the trick. So everybody knows the Poisson distribution, which is p of x, is basically 1 over x factorial, x to the lambda, lambda to the x, e to the minus lambda. Right? That's how you would typically write your Poisson distribution. Now let's take a logarithm of all of this and write it as follows. Okay, well actually we're going to keep the 1 over x factorial because it doesn't depend on any parameters. We have times e to the x times log lambda minus lambda. Okay. So now we're going to make a variable substitution. We're going to substitute log lambda for our parameter theta. And this yields p of x equals 1 over x factorial x of x times theta minus e to the theta. This is the expression of the Poisson distribution in its natural parameters. Okay. So these two formulations are obviously completely equivalent. However, this will allow us to have a nice convex optimization problem, whereas that one might not necessarily give us a very nice optimization problem. That's the only difference. Now, what we have up here is 1 over x factorial. This is how you weigh the various instances in your domain. The good thing is that regardless of what you have up here, the connection between the expected value of x and the log partition function still holds. Essentially, that log partition function already encodes everything that's happening here. Or to make things a little bit more explicit, we still have that the expected value of x drawn from that distribution is the derivative d theta of g of theta. Now that is just d theta of e to the theta, which is e to the theta, which is e to the theta. Now that should look familiar because e to the theta, this lambda thing here, is usually the mean parameter of my Poisson distribution that I just plug in directly. And so nothing has really changed. Okay. Any questions about that so far? Okay, cool. So I think everybody's seen a normal distribution at some point. Most of you would have seen the Poisson distribution, and well, I mean, the interesting thing maybe about it is that you can, make it peak more or less close to 0. I mean, basically, if you have counted random variables, and those count statistics are greater, equal, and 0, eyeball them, compute some histogram, and in some cases, the Poisson distribution may very well be a good approximation for that. There are a couple of others. There's, for instance, the beta distribution, and the beta distribution is a distribution over one parameter, maybe a number between 0 and 1. And you can make it as, smooth, basically as even as possible, so the uniform distribution would be example of that. So it's basically x to the alpha minus 1, 1 minus x to the beta minus 1, and then it's suitably normalized. This is the beta function, and that's where gets its name from. And you can make it as much peaked in one or the other direction. Okay. It actually has a very nice property, and we'll get to that in a moment. Namely, it is the conjugate to the binomial. So when you sometimes hear people write about beta binomial, or gamma Poisson, or multinomial Dirichlet, that's what they are referring to. And I'll show you with a bit more math later on how those things are related. Because it's actually very easy. So don't be scared by the names, because the math underlying it is actually very simple. Okay. So the interesting thing is it gives us a distribution over this one number, right, between 0 and 1. And you could say, well, hey, this looks, like the probability of an event. And so, we effectively have a distribution over probability distributions. Well, for this one single number, this looks very much contrived. For the Dirichlet, this is much less contrived. So for the Dirichlet distribution, it's a distribution on the simplex. So basically, it's distribution over numbers that add up to 1. So you could clearly use it as a probability distribution. And there's actually the infinite dimensional extension. It's called the Dirichlet process. And so if you take one of the non-parametric base advanced modeling classes that maybe Mike Jordan might be offering, or maybe it's in his seminar, you would have probably seen a lot of this stuff worked on, or maybe Tom Griffith might have talked about it in his class. So what you can do here is you can basically get distributions where, okay, if you get something from the middle, well, that just means that all three means occur with equal probability. And you can skew the distribution of the distributions in such a way that you have something that maybe only almost draws from, one class and nothing else. So you can really play with that quite efficiently. Now, before we look at the math that goes with it, let's go briefly through maximum likelihood. So the first thing that we're going to look at is the negative log likelihood. So if you remember, we have that P of x parameterized by theta is e to the phi of x dot theta minus g of theta. So now, if I draw an M sample from that, so it's an N sample on my slide, okay? So therefore, P of all the x's parameterized by theta, if I draw them independently and identically, is given by the product y going from 1 to n p of xi parameterized by theta. Right? So that should be nothing shockingly new to anybody here. Now then we go and plug this equation down here. Right? So we take this and plug it in here. And that gives us, since it's an exponent, I can take the product and pull it into the exponent, which gives me a sum, e to the sum I going from 1 to n phi of xi dot theta minus g of theta. Of course the sum goes away. So if I want to maximize this, pardon?
So isn't it n g of theta?
Pardon?
Isn't n times g of theta?
That's why I put those brackets around.
Oh,
If I were, yeah, sorry, the font size is too small. It would be g of theta times n if I didn't do that. You're absolutely right. And this actually has an interesting consequence. Because if we now want to maximize this, so we could go and minimize the negative log likelihood. Okay. So I have a minimization problem, and this is a convex one. Can somebody tell me why minimizing the negative log likelihood is convex? So basically, why is the negative of that a convex function?
G is convex.
Correct.
Either one doesn't matter.
Perfect. Yes. That's the idea. G is a convex function. That's the log partition function. Because the second derivative of it gives me the covariance, and so it must be convex. This is linear, so the sum of a bunch of linear functions is linear, and it's automatically convex. Okay, so we minimize, now in this case, n times g of theta minus the sum going from I equals 1 to n phi of xi of theta. By the way, who is doing the sliding, the scribe for today? Are there any volunteers? Okay, no scribes today. It's a free 5 points, right? Good. So, then you just all have to take notes. That's fine. So, if we minimize this, the first thing I can do is I can equivalently divide by n. So I get g of theta minus 1 over n, the sum. The second thing that I can do is I can swap the summation within a product. Right? Because inner product is linear. So we're going to get inner product. As a matter of fact, I can even plug the 1 over n in here. Inner product between 1 over n, sum I going from 1 to n phi of xi. Now this looks awfully similar to an average, right? As a matter of fact, it is an average, right? And this is the log partition function. Let's take the derivative. What happens? So let me just call this thing mu hat of x. This is like an empirical average of the sufficiency system. And if I take the derivatives, I get that d theta of g of theta minus mu hat equals 0. However, I know that this thing here has to be the expectation, just by the property of the exponential family. So I get that the expected value of phi of x has to be equal to mu of x. Okay. So this is our maximum likelihood estimate. So here's just on the slide what we have. So now, using this, it's trivial to, for instance, come up with a recipe how to estimate the parameters in a normal distribution, right? We go and compute the means and the second order moments, or in this case the covariance, and we then just go and match the parameters. So it's very straightforward. Okay. Now, let's think about what this actually means. And this is where we're going to get to conjugate priors. So, unless we actually have a lot of data, what we did so far isn't going to get us very far. Right? Remember from last time when I showed you even for a dice with 6 possible outcomes, you needed maybe 60 to 120 instances to get anything that's even remotely close to being a good estimate. And that's a problem because, well, at the end of the day, we probably won't have that much. Let's say I want to do something interesting with documents, and I might have, a vocabulary of a couple of 100,000, maybe 1 million words. Then, this would require that I would have between 10, maybe 100 million documents in order to get even just something interesting in terms of the individual word frequencies. And that's not very realistic. On the other hand, we also know that, if we use proper Bayesian reasoning, we can impose a prior. And by using this prior, we can come up actually with a better estimate of what we should expect. This is equation here. So P of theta given x, it's P of x parameters by theta times P of theta proportional to that. Now, one question is, of course, how should we construct our P of theta? So one way to construct it is to say, well, hey, this parameter theta beta ought to be small. And this will give you actually, as we'll see much later, Gaussian processes, for instance, or sparse coding and other things. So I basically just have that P of theta is e to then some interesting norm of theta. So if you've been used class, you would have probably, I don't know whether she's teaching that, but if she teaches sparse reconstruction, you would have probably seen objects like this in her optimization problems. Now, the question is more, how would we actually construct something that is a nice conjugate prior, nice prior, in such a way that our optimization algorithm keeps on working. More interestingly, can we design a prior for which, if we already coded up our maximum likelihood estimator, we won't have to change any of the code, but just the data a little bit, and we keep on using the same algorithm. And, well, a reasonable assumption on the prior is that it just behaves like additional fake observations. And that's exactly what we're going to do. We're going to add, we're going to assume that P of theta is proportional to P of x fake given theta. Right? So I can just, dream up some, fantasize some data. And so therefore, P of theta given x, that's the posterior now, proportional to the data likelihood times this fake likelihood of a prior. And since they are all assumed to be IID, well, this is nothing else than just taking the union of the real data and the fantasized data and estimating our parameter with maximum likelihood accordingly. This is all you really need to know to understand conjugate priors. Everything else is mathematical gymnastics, and we'll get to that eventually. But in order to understand how a Dirichlet works, or a beta, or a gamma distribution, or a Wishart, where they come from, this is the key idea. It's basically fake data. And so you can then ask, how would you do inference? And you can just right away read off from this equation here what you need to do. Because when we had an empirical average before, we now replace this by, well, we need to make a larger average over true data and fantasy of, well, the data that we've actually seen and the data that we've dreamt up. More specifically, I don't even need to really go and come up with individual instances. Let's take our dice, right? I don't have to come up with individual instances of a 1, a 2, 3, 4, 5, 6. I can just say, well, I expect all outcomes to be, equal with probability 1 over 6. And I just pick the constant vector with 1 over 6 in each of the entries. That's mu naught. And then the only other naught that I need to set for our dice, for instance, is, well, how many times do I assume I would have seen that? So if I play with a friend, and I know I can really trust him, I would probably set m to be maybe 100, right? On the other hand, if you go to some very shady place where you can't be sure that you're not going to be ripped off, then, m equals 2 or 3 might be a more reasonable choice. So your prior is, in this case, explicitly a way of encoding data that you think you might have seen, or data that you might have seen in a related experiment. So this is where a lot of engineering comes in. Now let's be a little bit more specific.
Can you explain why
Sure.
P theta is proportional to P x fake given theta?
That's my modeling assumption. So that's theta. This is my modeling assumption. I'm assuming that my prior should look like a posterior on fake data.
Well, that's a likelihood, right?
That's what?
That's fake given theta is a likelihood, right? It's a fake likelihood.
Well, I'm except that I'm now treating it as a function of theta. So I'm treating my likelihood with respect to some fake data as a function in theta, and I have to normalize it suitably such that it, works out into a proper probability distribution, and that's where all the nasty equations come from. So if you have nothing better to do, I suggest that at some point you look at, what a Gauss-Wishart conjugate distribution looks like, and it will probably fill your screen at least the full width, possibly wider. It looks ugly, but it's fully mechanical, so a computer algebra program would be able to compute that for you. And so don't be scared by the algebra here. I mean, conceptually, the important thing is you want your prior to look like a data likelihood after having seen some fake data. So let's see what it looks like in practice. Let's just estimate things for a Gaussian. And just to make things reasonably easy, I've just picked the one-dimensional case, but it wouldn't really matter here. So our sufficient statistics are x and x squared, right? And the mean and variance are of course given by mu is e, it's just the expectation, and sigma squared is just e sub x of x squared minus the squared mean. Okay. Now, let's go and actually come up with our maximum likelihood estimate. That's what we would do. Sum of the squares minus the mean squared. Okay. And now that we have this, see, these are basically given by our sufficient statistics. We can go and plug in our maximum posteriori estimates. So I'm going to work out in a bit more detail where this comes about. Does anybody have questions about this equation here? Is this just, estimating parameters in a Gaussian? So nothing special is happening here yet. Any questions? No. Good. So what we're going to do is, we're going to pick as our fake data which has zero mean and, in this case, unit variance. So my mu naught is going to be 0 and 1, and I'm going to give it a weight m naught. Okay. So therefore, so this is my mean in the space of sufficient statistics, and that clashes a little bit in the notation with the mean of a normal distribution. So those two things are unfortunately different things. Apologies for that confusion. So what we get is that we then have, sum over I going from 1 to n phi of xi. And then we add to that m naught times 0 and 1. And we have to divide all of this by n plus m naught. Now these guys in here are the pair xi and xi squared. Okay. And so we know that the first coordinate here gives us our mean of the Gaussian, and the second coordinate allows us to compute the variance. So this sum here plus 0, well, I just need to keep the first part. So this is then, 1 over n plus m0 sum over I xi. And for the second part, well, I have the 1 over n plus m0 sum over xi squared plus m0 over n plus m0. Now that's exactly what we have here. And then we just use the first term as the mean, and we use the second term minus the mean squared as the variance estimate.
Can you explain what's the fake data in this case?
So I could make up some other fake data. So the fake data in this case just assumes that it's been drawn from a normal distribution with zero mean and unit variance. Now, if I was going to measure maybe the voltage in a power plug, and let's assume it's actually switched on, right? Then beforehand you have a pretty good idea that you're probably going to see something like 110, 115 volts, and maybe you know that in the United States the voltage maybe varies by 5 volts or so maybe we use that as our standard deviation, and we just use that as a prime. And then I'm going to measure on a few sockets in the building what the voltage is. I use these as my actual voltage measurements, add a fake prior to it, and I get an overall estimate. Now for univariate Gaussians, that's completely overkill because you only have really 2 parameters, and you're going to get all the data very quickly. Once you go to maybe 1,000-dimensional Gaussians, things get a lot more interesting than you actually need it. Now here comes something that's technically a little bit more complicated. It's called collapsing. So this is where a lot of the slightly more complicated expressions come from if you talk about conjugate priors. So, we after all have this, P of theta is proportional to x fake given theta, and, well, implicitly in making that assumption it means at some point we should have been able to compute the integral d theta. Otherwise, well, you can't really do many interesting things with that. So, however, you can also use it as a prediction for prediction purposes. Because if I want to estimate, what's the probability of x, given that I've already seen all that data, and by Bayes' rule, that's very simple, right? It's p of x, given that parameter, times p of that parameter theta, given all the data. Now that posterior, can be written out as p of x given the data, times p of x fake given the data d theta, and of course it's proportional. I just need to make sure it indeed integrates something. Now, what we have here are essentially 3 likelihood terms. Right? I have the new instance, I have the data that I've actually seen, and I've got my fantasy data. And then I just need to solve this integral. So you can do fairly interesting things with that. So there's, for instance, an algorithm called Bayesian sets by Catherine Heller and Subin Garamani. I think they're the only two authors on it. Okay, write it down. And that uses this insight. So I mean, this is a very obvious thing, right? This paper is, I think, maybe 4 or 5 years old. And what they managed to do with this is actually extend sets and lists of objects in a very natural way. So they basically take collections of instances, let's say movies, in groups. And then the question is, how would you extend those groups in such a way that you put more related movies into the same group? So each of those movies have a set of attributes. I think in their case they use some co-occurrence with words and so on. And then the question is essentially for a new word or a new movie, into which of those bins should it go? And they decide onto the bin based on this expression. And you get something which, at least at that time, was, at least so they claim, better than what I think Google Sets or Listmania was able to achieve. And it's a very, very simple idea. It's quite powerful. I mean, they used a very simple distribution, just multinomials. To my knowledge, there I think was even a startup which tried to, make money out of this idea. I don't know what became out of the startup, but these two guys weren't involved in it, that I know. Maybe they got bought up. So you can see that with essentially 100 years old technology, you can still write cool papers, do really nice things, and even get funding for a startup. Yeah. So let's look at things at a slightly smaller scale. So let's just toss our dice again, and right. So what we get is that for our maximum posteriori estimate, this maximum likelihood, and you can see that for our math estimate, those numbers move closer to 1/6, and how close they move to 1/6 depends very much on how much we smooth. And that makes a lot of sense. So this, by the way, is a rule that's called Laplace smoothing if you just add a count of 1 to everything, and that's over 100 years old. You would have probably done a similar thing if you ever processed text, you did word counts, and at some point you had to take the logarithm. And you squinted at the numbers and you thought, yeah, logarithm of 0 is really bad. Let's just add 1 to all the numbers and pray that our algorithm works, right? Who has done this before? Okay, about half the audience. And then you felt slightly awkward, I'm doing something horrible to the data. No, actually you're not. You're just doing Laplace smoothing. So you're doing something very principled. You just didn't know it. So for an honest dice, well, you can see that actually the map estimate is, much smoother. The slightly worrying part, of course, is for a tainted dice. So in this case, I pick, a dice which, for which the first 3 events were of a much smaller probability, then next 2 were smaller yet again, and the third one was large. And it takes the math estimate a fair amount of data to pick up what's going on. And I think I picked the first 3 probabilities at 0.1 and then I think 0.2 and the rest just to fill up things. So basically be careful about your prior. If you oversmooth, you're not going to detect anything bad for a long time.
Just using the same fake data in this case?
Pardon? It's using the same fake data in both cases. It's just that this uses a map and this is uses a maximum likelihood estimate. So this is basically just counts divided by total counts. This is counts plus fake counts divided by total counts plus total fake counts.
So for the fair dice and the tainted
Yes.
dice, are you using the same?
So I'm using the same prior.
Okay.
Yeah. So basically I've stumbled into a gambling saloon that's cheating and I haven't noticed it yet. So then it takes me quite a while to figure it out. Okay. Now these are not the only priors you might encounter, and so a little bit of what I just told you before is you could just have the idea that all your parameters should be small. Quick question to the audience: why is it a good idea if these theta should be small? Besides the fact that it's computationally convenient. If I have an exponential families distribution and I have a small theta, what does it mean? Let's look at the probability distribution again. So P of theta, parameter P of x, parameterized by theta is e to the phi of x of theta minus g of theta. What does it mean if this guy here is small? Correct. That's exactly what it is. It just means I have a distribution that's very close to a uniform distribution. Now, uniform distribution may actually be a really good choice. If I don't know anything about my problem, I mean, the best thing I can say is, well, everything is about equally likely, subject to maybe some measure transformation and so on. And that's effectively what those priors are encoded. And this gives me usually a nice convex optimization problem that's smooth, and this will give me a non-smooth convex optimization problem. And you can write several papers and probably get tenure based on coming up with really clever algorithms for this. It's a big industry. And you can actually prove very beautiful things about this scheme. That's also big industry. So let's just see how this all fits together. Well, our posterior here is just going to be, our likelihood, so P of xi given theta. The bracket, of course, goes around here, times P of theta, which, is e to the, now here we have a concave function. Well, this is convex, and this is linear. So now we get a simple convex minimization problem with a quadratic penalty. You may have seen this thing also under the name of penalized log likelihood. So you can therefore get this optimization problem. So this would be usually the penalty on your log likelihood expression. Okay. So that's about all I wanted to say about exponential families for now. We're going to do a fair amount of this later on when we look at classifiers, regression estimators, a lot of conditional estimators, and then we'll do a little bit of graphical models as well. But basically, when we do conditional random fields, regression, and so on, this is essentially the standard tool that we will be using. Okay. And I just want to essentially unscare you because there is really not much, conceptual difficulty in it. Just sometimes gives you very unwieldy equations. If you look at that, okay, that looks a little bit messy, but that's really what's happening up here. Okay, so I think now it's time for some break. If you have any questions, and